Hello and welcome to the video. So in previous video, we tried to discuss two-stage op-amp in great detail and also the positions of its poles and zeros, and we tried to adjust them in order to get sufficient phase margin, and we also looked about the stability. So in this video, let's consider op-amp we discussed earlier, where we have our two-stage op-amp and we have our transconductor. So uh, this is the basically op-amp we are using right now over here. And for this circuit, we have our DC gain, which is basically GM1, GM2 by GO1, GO2, and where omega U lies at GM1 by C. So we have our first pole intuitively at this position, and our second pole intuitively comes at this position. So our pole is nothing but some conductance divided by some capacitance, and let's say intuitively we can break down our P2 at this, and we know that CL is very great. CL is very greater than C1, so does GM2 is very greater than GO2. So intuitively we can say that our P2 lies at GM2 by CL. Also, we have our omega u of our main transconductor, and we have omega u2 of our current controlled voltage source, and we also are getting 0 at right hand part, which is gm2 by c, based on our transfer function. So we know that our omega u is nothing but gm1 by c, and our omega 2 is nothing but gm2 by CL. So now we know that to implement our op-amp, we took an transconductor and followed it by a current controlled voltage source whose unity gain is omega u2. Now our feedback functionality will be in working condition until the frequency omega u. So when we see the body plot, so our feedback functionality or our curve will be functional until omega u. After that, we reach the 0 dB range, and then our gain falls beyond the 0 dB. So after omega u frequency on the body part, the loop gain becomes very small, and thus clearly the feedback does not have the function as desired. So this means that our omega u2 must be sufficiently larger than the frequencies of interest. So what are the frequencies of interest? So our frequencies of interest is basically omega u and the frequencies below that. So basically our omega u2 should be greater than omega u, and we have the values gm2 by c2 and gm2 by cl, and gm1 by c for our omega u2 and omega u, and thus we can say that our gm2 by cl should be greater than omega u, and this is what we intuitively said where our pole p2 lies. So we can say that p2 should be very greater than omega u, and that's what we are assuming the must condition, that our pole 2 should lie at very higher frequency as compared to omega u, which is our unity gain frequency. So now our concern is, so we have a right hand plane 0, and that 0 obviously will give us a phase lag, and we have to think that is there a way to eliminate the effect of that pole or the lag caused by the 0, not pole 0. So let's consider our second stage of our original op-amp, which is only this stage. So it looks like this, and according to our polarity, current gm times v is drawn from this transconductor, and hence we have voltage across the capacitor. Along with that, we have voltage at this part, and the voltage across the capacitor is gm1 times ve, which is the current divided by its resistance, or basically conductance, which is 1 by sc. So we can say that gm1 times v, this is the current which passes through capacitor c, and it should come from the transconductor, and for that to happen, we should have a voltage across the inputs, which is which has to be current through the OTA and the transconductance of the OTA, basically GM1 VE divided by GM2. So this is the amount of voltage which should be uh, across the inputs of the OTA for our current GM1V to be flown by the capacitor. And we know that from this, if we consider GM1V by SC, so this is the ideal situation. This is the exact voltage we want at V naught, but the voltage at V naught is not ideal, and it is something, this voltage plus the voltage over here, and both voltages has opposite signs, so there is a difference between these two voltages which comes at V naught. So let's look at the values. So basically V naught is nothing but GM1 times VE is common between these two voltages. This is all voltage at input and this is voltage across capacitor. So we take GM1 VE common, and inside we have 1 by SC minus 1 by GM2. So why minus? So we have polarity minus to plus and we have polarity plus to minus. So this is the basic circuit theory equation. From that we can derive that GM1 times VE, and when we solve this term a little further, so this is what something we get, and in the numerator this is the exact term we saw in the transfer function which gave us the 0. So let's eliminate the 0. So to eliminate the effect of right hand pole 0, right hand plane 0, we have our transfer function, not transfer function, but we have our v naught from here, which is basically this term, and this is the term which is desired, and this is the term which is unwanted. So to cancel the effect of this term, to get rid of it, we have to add a plus 1 by gm2 term in some way, like somehow we have to add plus 1 by gm2 to this whole part, or let's say, which means basically to the whole v naught we need to add a voltage of gm1 ve times 1 by gm2. So gm1 ve times 1 by gm2 volts in plus, so that this minus effect gets cancelled by a plus effect. So there is a very simple way of doing this. We have this circuit, or let's say we have this in our stage 2, and basically we at our v naught, two voltages are contributing, voltage across this and voltage across this. So these two voltages are contributing, and along with that, let's say we want this extra voltage. So for this extra voltage, let's introduce a resistor, and whose conductance is basically 1 by gm2. So what will happen now, that there will be three voltages which will be contributing towards the v naught, and basically v naught will look like this voltage, this voltage, and this voltage, and these are coming from the voltage across this resistor, voltage across the capacitor, and the voltage across the input. So basically our v naught, and thus due to this resistor, the voltage, the unwanted part is thus nullified or eliminated, and our v naught comes out to be gm times ve divided by sc, and this is the exact thing we wanted, and we achieved it by placing a resistor in series with c. So we can eliminate the effect of right hand plane 0, and I think, yeah, we are successful in it. But let's talk further. Let's talk what happens in reality. So, but the value of the register might get shifted. So it's not easy, or let's say it's not practical to make exactly same value register, and in a circuit while it's working, or in a system, there can be a chance where the register value might get shifted a little up or down. So let's see what happens, and let's consider the value of register as rz as of now, and let's consider the value rz. So we know that the contribution towards v naught is from these three voltages. So we'll write v naught equals to this equation, and we knew how it came from. After solving a little bit, we can say that we are getting a 0 at this position, where it is minus gm2 by gm2 rz minus 1 times c. So now this is a left hand plane 0, where we can say that when rz is equals to 0, which basically means there is no RZ. We go back to our original case, and at that time when we put RZ equals to 0, so this minus sign gets cancelled by this minus 1, and we get our pole at GM2 by C. Hence we have proved the sanity check. And now let's talk that if RZ is exactly equals to 1 by GM2, then the 0 moves to infinity. From this equation we can say that 0 is shifted to infinity, and thus we have eliminated the 0. And when the value of RZ is even greater than 1 by GM2, then we get the 0 in left hand pole, which offers a phase lead, enhancing the stability. So I think this is working in our favor. So let's talk about that. So yeah, so now let's talk about that. And we have a two-stage op-amp with right hand plane zero cancellation. So this is how our circuit will look like, in which we have two nodes. We have this node and we have this node, and these two nodes are associated, and we can make RZ which is equal to 1 by gm2 to shift the 0 at infinity, or we can also increase its value as we looked over here, and achieve more than 1 by gm2 value, and where we will get a 0 in left hand plane, and it will give us a phase lead. So it might work in our favor, but let's talk about it. So even though it sounds good to make higher value RZ to get a phase lead, and but it's not a good idea. And let's talk why. Let's see why. So in the above circuit over here, in this circuit, due to RZ, due to the RZ which came between the loop of C1, C, and CL. So now we have three independent capacitor loop voltages. So basically we have three independent poles, and we need to investigate the pole P3 because we have investigated first two poles. But now due to the RZ which came in between these three capacitors, so now there are three independent capacitor loop voltages, and we get a extra pole which is P3, and we need to investigate the pole P3 introduced while eliminating a 0, which will cause a phase lag. And we need to see that this phase lag due to P3 is ruining our desired output or not. So writing the node equations again for this circuit, and in second stage feedback, instead of SC, while writing a node equation in second stage feedback, instead of SC, now we have SC divided by 1 plus RZ SC. And this is a basic circuit theory equation. So in our admittance matrix over here, instead of SC, we will now be getting SC divided by 1 plus SCRZ. And after writing the node equations, we are only interested in V naught. So what we will do is we will take the determinant of Y matrix. We will just replace this column with these values, and in the denominator we will take the determinant of Y matrix, and we will get a third order equation from this. And from the transfer function we will get a 0 will be at gm2 divided by gm2 rz minus 1 into C, where we have discussed these conditions already. So the transfer function will be in the form of a third order equation. And what we can do is over here, we can again make an algebraic approximation, and we can take two terms at a time, these two, and equate it to 0, these two, and equate it to 0, these two, and equate it to 0, and we will get three linear equations. And the solution to this will be valid only if the approximation will be that the three poles are far away from each other, and properly far away from each other, and only if that is the approximation, then only we can make the approximation and solve the third order equation in this way by taking three linear equations. So instead of doing that, and instead of increasing the complexity, let's discuss it in an intuitive way for the locations of pole. anyway we are interested only in the locations of pole. So this is our circuit with our RZ to eliminate the 0. So first pole will be associated with GO1 and the capacitances related to this node, and it will be same as before but also with some terms due to RZ, and which won't be that dominating. Second pole will be due to GO2 and the capacitances related to this node, and the third pole would be due to RZ and the capacitances associated with RZ. So basically, let's say it has nothing to do with the input voltage. So let's take the input voltage 0, and thus this transconductor vanishes away, and so does this one, and our circuit basically becomes the circuit like this. We have a RZ like RC circuit, and we can say that our third pole will be at -1 by RZ, 1 by C, plus 1 by CL, plus 1 by C1. So this is basically all the capacitances related to this node. So basically, to eliminate 0 at GM2 by C, we introduced a pole which is at this value. This means the pole we introduced is at a higher frequency than the 0 we eliminated. So we are still safe because P3 is at higher frequency, and thus resulting in a phase lag which is less and tolerable. But the P3 should be at higher frequency, and it is at higher frequency. Hence, it is not wise to think of making R2 very large and moving the 0 to left hand plane, because then P3 will move to lesser frequency, causing the more phase lag. So how can we say that? Because we are saying that 1 upon Rj. So basically, we are making it to GM2. And now if we say that we want to increase the value of Rj, so Rz, so we are basically saying that we have to decrease the value of GM2. And if we decrease the value of GM2, then this pole will shift to lesser frequency values, and thus it will give more phase lag, and which won't be tolerable. So here only we are considering that it is at higher frequency, we should keep it at higher frequency. So I think it is not wise of making RZ very large and moving the 0 to left hand plane, because then P3 will move to the lesser frequency, causing more phase lag. Also, by putting RZ very large, the phenomena of pole splitting will not occur, and we have discussed the phenomena of pole splitting in previous videos. So, and it helped us in stability as well. So that phenomena will not occur if we put the value of RZ very large. And it's okay to make it 1 by GM2 and try to cancel the 0, but it's not wise to make it very large. And also, it is very hard to make the value of RZ exactly equal to 1 by GM2, but we must design the system wisely. So first, we had a single stage op-amp. Then for better performance, we made two-stage op-amp, in which we use single stage op-amp in feedback to create a current controlled voltage source. So instead of using a single stage op-amp in current controlled voltage source, we can use two-stage op-amp to make a current controlled voltage source. So basically, while creating a current controlled voltage source, instead of single stage, now we have used two-stage op-amp. So this is how its circuit will look like, in which this part is our current controlled voltage source. So now this is also, by the way, called as three-stage nested Miller op-amp, where our DC gain will be just the consecutive multiplication of GM1 R01, GM2 R02, and GM3 R03. And we have three independent state variables. So basically we have three nodes. Let's say one node is at V1, one node is at V2, and one node is at V1. So V1, V2, and V0. So V0 is our output. So basically, let's derive some conditions, but intuitively. So we can say that unity gain frequency omega u of the op-amp we are trying to realize is GM1 by C. Let's take the value of let's not consider the value of negative feedback loop. And we know that our GM2 by C2 must be greater than GM1 by C. And this is the condition for current control voltage source to work the way we desired. And our omega U for two stage used for current control voltage source is basically GM2 by C2. So this is our GM2 by C2, and this is the unity gain frequency which we decided for our two-stage op amp, and which is our current control voltage source. So the omega U for the current controlled voltage source within the two-stage op amp is GM3 by CL, and hence we should take care of this fact that GM3 by CL should be at greater value than GM2 by C2, which should be again at a greater value than GM1 by C. So to increase the DC gain, it's okay to make multiple stages. But again, the transfer function for this circuit is complicated with the denominator having 3-degree equation. It is hard to find exact position of zeros and poles intuitively, but intuitively we can say that the omega loop of each stages should be greater than the original stage, and this is the omega loop of our op amp which we are actually trying to realize. And if we have more than three stages, we realize lower and lower value of gm1 by c, and there is lower limit for gm1 by c in CMOS technology. So hence it is not wise to go higher stages, as even though it will give us a higher DC gain, but omega U will be at lower frequency value and we have a lower limit. So it's not wise to again make many higher stages. So I think we have made a proper discussion on these concepts, and I think that is enough for this video. Thank you for watching.